Welcome to Graphical Descriptive Statistics, Making Data Speak. Here's a brain bender to start your day. A study once showed that more students passed an exam when fewer of them had studied. Wait, what? How is that even possible? It sounds like studying is bad for you, but here's the twist. The data was being looked at all wrong. Lump two groups together and the truth disappears. Separate them out and suddenly everything makes sense. That phenomenon has a name, Simpson's paradox, and by the end of this episode, you'll know exactly how to spot it and never be fooled by it again. Stick around. Here's what we're covering today: how to build frequency tables, how to read bar charts and pie charts, how to create histograms and dot plots, how to interpret skewness, how to make stem and leaf displays, how to read crosstabs and side-by-side bars, how to spot Simpson's paradox, and how to use scatter plots to find relationships in data. That's a lot, but trust me, it's gonna fly by. Let's go. So why do we even bother with graphs? Why not just read the numbers? Here's the thing. The human brain is wired for pictures. We can stare at a spreadsheet with 500 rows and see nothing. But show us the right chart? Patterns jump off the page in seconds. That's the superpower of graphical descriptive statistics, turning raw data into a visual story that anyone can understand. But, and this is important, that power cuts both ways. A badly designed graph can hide the truth just as easily as it reveals it. Truncated axes, missing labels, weird three-dimensional pie charts that make small slices look huge. These are not just aesthetic problems, they are misleading. They can change decisions. They can change policy. So our job today is to become fluent in the language of data visuals, both how to read them and how to build honest ones. Because when you look at a chart, you should always ask yourself, look at the picture. What is it really telling me? Let's start with the foundation, the frequency distribution. Imagine you surveyed 15 students about their favorite pizza topping. The answers: pepperoni, cheese, veggie, pepperoni, pepperoni, cheese, veggie, pepperoni, cheese, pepperoni, veggie, cheese, pepperoni, pepperoni, cheese. Now, what do you do with that pile of words? You sort it, you count it, you organize it. A frequency distribution is a table that shows how often each category appears in a dataset. That's your technical definition right there. And it has three key columns. First, frequency, the raw count. Pepperoni shows up 8 times. Cheese shows up 5 times. Veggie shows up 3 times. That's your frequency column. Second, relative frequency, the proportion. Divide each count by the total of 15. Pepperoni is about 0.53, just over half. Third, percent frequency. Multiply that proportion by 100. Pepperoni, 53%. Think of it like sorting M&M colors into little piles. Count each pile, divide by the total. Boom, frequency distribution. That table is the backbone of almost every chart we'll build today. Look at the picture. It starts right here. Now let's make that table visual. Two classic options, the bar chart and the pie chart. A bar chart uses rectangular bars to represent each category's frequency or percent frequency. Simple, clean, powerful. Pro tip: order your bars from tallest to shortest. It makes comparisons instant. Always label your axes, and please, never ever use a three-dimensional bar chart. The depth adds zero information and makes everything harder to read. A pie chart uses slices of a circle to show each category's share of the whole. It's great for one question: what proportion does each piece represent? But here's the catch: comparing two pie charts side by side. Terrible. Our eyes are bad at comparing angles. Bar charts win that battle every time. So here's the rule of thumb. Use pie charts to show parts of a whole for a single snapshot. Use bar charts to compare categories or track changes. Look at the picture and ask, what comparison am I trying to make? Okay, now our data gets numerical. What if instead of pizza toppings, we have exam scores? Let's say we have 30 exam scores ranging from 50 to 99. We can't make a bar for every single score. That's too many. So instead, we group them into bins, also called classes. Each bin covers a range, 50 to 59, 60 to 69, 70 to 79, 80 to 89, 90 to 99. Each bin has the same width, in this case 10 points. That's your class width. The midpoint of each bin, like 64.5 for the 60 to 69 bin, helps us represent the whole group with one number. Now we count how many scores fall in each bin. That's your frequency. Divide by 30 for relative frequency. Multiply by 100 for percent frequency. And here's a bonus, cumulative frequency. Add up the frequencies as you go from the lowest bin to the highest. After the 70 to 79 bin, your cumulative frequency tells you how many students scored below 80. Super useful for understanding how a group is performing overall. Instructor tip: choosing bin width matters enormously. Too wide and you hide the shape of the data. Too narrow and you get noise. Aim for 5 to 10 classes as a starting point. Now let's visualize those quantitative distributions. Two great tools: dot plots and histograms. A dot plot is exactly what it sounds like. Each data point gets one dot plotted above a number line. Imagine lining up everyone's shoes by shoe size. Each pair of shoes is a dot. You can see every individual value. Dot plots are perfect for small datasets, say under 30 observations, because you preserve every single data point. A histogram looks like a bar chart, but it's built for quantitative data grouped into bins. Here's the key difference. In a histogram, the bars touch. No gaps. Because the data is continuous, there's no empty space between 69 and 70 on an exam. When should you use which? Small dataset, individual values matter. Dot plot. Larger dataset, you want to see the overall shape. Histogram. And that shape, well, that's our next stop. Look at picture. What shape is your data making? Here's a chart type that doesn't get enough love. The stem and leaf display. Take our exam scores. The tens digit is your stem. The ones digit is your leaf. So a score of 73, stem is 7, leaf is 3. A score of 78, same stem, leaf is 8. You line up all the leaves next to their stems, and suddenly you have a sideways histogram that still shows every raw data value. That's the magic of stem and leaf. It gives you the shape of a histogram and keeps the original numbers intact. You can read individual scores. You can find the median easily. It's like a histogram that didn't forget where it came from. Great for classroom use, great for quick analysis. Okay, back to that histogram shape. This is where things get really interesting. Skewness describes the asymmetry of a distribution. That's your technical definition. And it has three flavors. First, symmetric. The left side mirrors the right. Think of a classic bell curve. The mean and median are basically the same. Clean, balanced. Second, skewed right, also called positively skewed. A long tail stretches out to the right. Think income data. Most people earn a moderate amount, but a few billionaires pull that tail way out. The mean gets dragged toward that tail, making it higher than the median. Third, skewed left or negatively skewed. The tail goes left. Think exam scores on an easy test. Most students score high, but a few struggled. The mean gets pulled down below the median. Now here's why this matters practically. If your data is skewed, the mean can be seriously misleading. A skewed right income distribution means the average salary sounds much higher than what most people actually earn. Look at the picture, and always ask, is that tail pulling the story somewhere the numbers alone won't tell you? Now let's compare groups. This is where cross-tabulations, or crosstabs, come in. Imagine you survey 100 college students. You ask two questions: what's your major, and what's your preferred study method, solo, group, or online? A crosstab organizes both variables in a table, majors as rows, study methods as columns. Each cell shows a count. But here's the catch: raw counts can be misleading if group sizes differ. That's why we convert to row percentages, or column percentages. Row percentages tell you, within each major, what proportion prefers each method. Column percentages flip it. Within each study method, what proportion comes from each major. Now visualize it. A side-by-side bar chart puts bars for each study method next to each other, grouped by major. Great for comparing actual counts across groups. A 100% stacked bar chart converts everything to proportions. Each bar reaches 100%, so you can compare the composition of each group directly, even when group sizes are very different. Active learning moment. Here's your 60-second challenge. Grab any dataset with 2 categorical variables, build a quick crosstab, and ask yourself, do the row percentages tell a different story than the column percentages? Try it right now. What about the relationship between 2 quantitative variables? That's where scatter diagrams shine. Plot one variable on the horizontal axis, one on the vertical. Each observation becomes a dot. Now step back and look. Are the dots trending upward from left to right? That's a positive relationship. As one variable increases, so does the other. Think study hours and exam scores. Trending downward, negative relationship. As one goes up, the other goes down. Think absences and grades. No pattern at all, no relationship. You can add a trend line, a straight line that best fits the scatter of dots, to make the direction and strength of the relationship clearer. But here's the critical warning. Correlation is not causation. 2 variables moving together does not mean one causes the other. Ice cream sales and drowning rates both go up in summer. They're correlated. But ice cream doesn't cause drowning. There's a lurking variable. Hot weather, doing the real work. Always look for that hidden driver before jumping to conclusions. Look at the picture, but think before you leap. All right, let's bring it home. 6 things to take with you today. 1. A frequency distribution organizes data into counts, relative frequencies, and percent frequencies. It's the foundation of every chart. 2. Use bar charts to compare categories, pie charts to show parts of a whole, and never use 3-dimensional versions of either. 3. Histograms reveal the shape of quantitative data. Always check for skewness before trusting the mean. 4. Dot plots and stem and leaf displays preserve individual data values. Use them when the details matter. 5. Crosstabs and stacked bar charts help you compare groups. Always decide whether row or column percentages answer your question. 6. Scatter diagrams show relationships between 2 quantitative variables, but correlation is never causation. And the bonus rule, the one that ties everything together, look at the picture. Always look at the picture. Ask what it's really showing. Ask what it might be hiding. Here's your call to action. Try a 5-minute demo. Pick any dataset, pizza toppings, exam scores, survey results. Build one chart and share a screenshot with the hashtag #MakeDataSpeak.